Hello, everyone. Welcome to this first edition of the Chaos Week. So we will wait for about 2 or 3 minutes to let all the attendees join and make themselves comfortable. I hope also that you had time to see the previous talks that were very interesting. If not, don't forget that you can watch them again on YouTube, on the WeScaleTV channel. There's a playlist for the Chaos Week. Et en français, bonjour tout le monde. Je vous remercie d'être venu à cette première édition de la Chaos Week. Donc, on va attendre 2-3 minutes, le temps que tout le monde nous rejoigne et se mette à l'aise. Donc, j'espère que vous avez pu regarder les conférences précédentes qui ont été très bien reçues. Et n'oubliez pas qu'elles sont dispo en replay sur YouTube si vous n'avez pas eu l'occasion de les voir. Donc, sur la chaîne WeScaleTV, il y a une playlist spécialement pour la Chaos Week. So we'll wait for everyone to join. They're probably off from the last talk, the previous talk, and jumping from one feed to the other. So we'll wait just a minute and then we start. All right. Well, welcome again. So I'm Alexis Morel. I'm a cloud builder at WeScale. And I would like to thank you all for attending this talk for the fourth day of the Chaos Week. It's the last talk of the Chaos Week. And I invite you also to take a look at the previous talk on WeScaleTV on YouTube. If you missed them, there's a Chaos Week playlist with all the talks. So, as you may all know, chaos engineering is now an expanding topic, and it is also very interesting for us at WeScale. So, for that reason, we wanted to share this with you via a free and online event that lasted 4 days. Well, our goal here was to make it accessible to you, make accessible some vision and some experts' insights and feedback on the chaos engineering topic. I would like to add that the chaos engineering has already been integrated as a discipline in many company strategies to help for them continuously improve their infrastructure resilience. And for that reason, I am very happy to welcome Karthik Satchitanand from Bangalore in India. Well, he loves classical music. He's also the co-founder of Chaos Native and as well as one of the core maintainer of Litmus Chaos. Karthik will be talking today about declarative hypothesis and observability in chaos experiments. So, hello, Karthik, how are you?
I'm doing great, thank you. How are you doing?
Yeah, I'm good, thank you. Well, it's a pleasure to welcome you on this first edition of the Chaos Week. And I'd like to thank everyone that is joining us today. I will take you now. I will let you take the lead now. And I wish everyone a pleasant conference. I will come back later for some Q&A at the end of the talk. Have a nice conference, Karthik.
Thank you. Hello, everyone. Welcome to this session. I think the first edition of Chaos Week has been really eventful. I got some of the talks. They're awesome. So I'm sure you must have had a great conference. I hope to do justice and maintain those standards in the last talk of this edition. So we're going to be talking about declarative hypothesis and observability in cloud native chaos engineering. Thanks for the intro. Like I said, I'm Karthik, one of the maintainers of Litmus. So let's go ahead and dive into this session today. The agenda is pretty simple, and the intro is already done. I don't want to dwell too much upon this. The agenda is really simple. We are going to take a look at a few slides. I don't have too much information on my slide deck. Prefer to do more of a live demo. We'll just take a look at the standard chaos engineering flow and how it looks like in the cloud native world. And we'll examine the role of hypothesis and how observability plays a very important part in aiding your understanding of steady-state hypothesis. We'll see what hooks the Litmus Chaos project provides. I'm sure all of you have by now got a chance to understand what cloud native chaos engineering is, what Litmus Chaos project does, etc. There have been some great talks before that. I'm sure you've just hopped off Uma's talk that's detailed the evolution of cloud native chaos and was talking about how Litmus came about and where we are going. So we look at what hooks this particular project or framework provides in your chaos journey for doing observability analysis and steady state hypothesis checks. Right now on my screen, I've got a slide which is a very simple schematic diagram that shows you a simplified chaos engineering process stripped down to its basic essentials. So you try and identify what this steady state is, the optimal operating characteristics, so to say, of your application or services. Then you go ahead and introduce chaos, you create a fault, and then you observe and basically go back to the drawing board and improve if there is an improvement to be made, or if things are good, you move on to the next fault or next chaos, and you just repeat this process or this feedback loop. The observe part of it is quite important because you could be observing with a specific intent. That intent is what we call as steady state hypothesis. The hypothesis is a set of expectations that you have around how your applications are going to behave, how they are going to deviate from steady state, how long does it take for the deviation to be detected or notified, how long does it take for it to revert to optimal characteristics, is that deviation within expected limits, is your service SLO being met while the chaos is introduced. All this is part of your hypothesis, broad hypothesis. Sometimes there are some very interesting orthogonal requirements or measurements that you make when you inject chaos on your infrastructure. Things like, are you getting the right notifications, for example, is also part of your hypothesis. So it's something that's very broad and diverse. I have just tried to expand that initial schematic diagram into a flowchart here. It's the same thing. I've just expanded that observe and improve section into a couple of items on the right-hand side of this particular diagram. We are explicitly stating here if the steady-state hypothesis is met. If it is, then your application is resilient to this fault or this scenario. If it is not, then you've found a weakness, or you probably might have the wrong expectation out of your system. The latter is very unlikely because you know generally what you expect out of your system. So if your steady-state hypothesis is not met, then that means there is a weakness found either in your business application logic or in your deployment environment or the core underlying infrastructure. There is some problem that you probably need to fix. Right. So how do you really define a steady state, or how do you arrive at this thing called steady state? When you build your application and you build it for a specific functionality, and especially in the cloud native world, it means that your application is a cluster of microservices maybe with very specific interdependencies defined. Your application or your services has what you would call as some service level objectives or SLOs. And these SLOs are actually derived from a larger set of goals around what your application is expected to achieve in a certain environment, something that you would term as SLAs. This is the business part of your metric or measurement. And the SLAs then sort of give rise to one or more SLOs, and these SLOs are then expected to or mapped to certain behavior, expected behavior of some service level indicators. So you have most commonly metrics used as the service level indicators, and you create some conditions or cutoffs against these metrics or service level indicators, which we call as service level objectives. So this is an oversimplification, but I'm trying to explain it this way for illustration purposes. So you've got some SLOs that you've created from an available set of SLIs. And what are those SLIs usually? You must have heard of these golden signals for SREs, things like the latency, your errors and error rate, the saturation, traffic being defined by different performance parameters. Or it could be something else completely that's very, very custom or native to your application, which is as important as the four other golden signals that we mentioned above. They are the standard ones that most SREs look at, but there could be something else that you're also measuring, which is equally important. In the Kubernetes world or the cloud native world, there are what we call as some auxiliary indicators of steady state. And why do we call them as auxiliary? Because they don't really fit into the traditional definition of a metric or a traditional definition of a steady state behavior. These are something that's come newly because of the cloud native paradigm. There are so many microservices, dependent microservices, what we call as downstream services. So which you would generally not find so much in a monolith kind of an environment. So the availability of those services, the statuses of certain Kubernetes resources, and this is very, very specific to Kubernetes. Nowadays, people are running their applications, complex applications, mostly stateful ones, using operators. So there are CRs that define the desired application state and operating characteristics. So there is an operator which reconciles that state and manages your application and then pushes information back into those resources, the status of those resources. So you might want to know and query those resources to identify whether your applications are behaving the way they should. So this is something that's new that's coming. These are also indicators of steady state. So there are diverse ways of looking at steady state. Sometimes, let's say your application exposes or provides a client, there is a CLI tool associated with your application, and that CLI tool is gathering some information and outputting some useful information, status flags that you want to query as part of steady state. There are diverse ways in which you can basically measure steady state apart from the standard metrics that you have. So when you're doing chaos experimentation, you might want to take a look at the entire spectrum of these indicators. You want to look at the traditional metrics. You also want to look at all these auxiliary indicators. You want to make sure that your SLOs are being met in every which way, and anything that leads to that. So for doing this, now you know what steady state is. We have a definition. But how do you measure that? You need the data sources, right? We talked about Kubernetes resources. We talked about metrics. You need an exporter, or you need some metric source. You need observability. That's what we're trying to say. Observability is critical in chaos engineering. Without the right observability infrastructure in your environment, you should not be probably venturing into doing serious chaos engineering. You might do more of it as exploratory testing, but you might not really find success, or you might not be able to derive the right return on investment, or you might not be able to get the right KPIs for your chaos engineering practice if you do not have observability aiding you in this journey. You need to have the right metrics, you need to have the right metric sources, you need to be writing that as part of your application stack. You need to be having the right APM tools. You need to be having the right dashboards. All that's really important. And observability has a lot of parameters, a lot of pillars, events, metrics, logs, traces. There are so many parameters or so many phases of observability. And that's really critical to chaos engineering. So you need to use these observability frameworks, or you need to use this observability infrastructure to measure your steady state and then get the right insights on whether your steady state hypothesis has been proven right or no. Now, there's also a small side note that I've put under this observability point, and this is something that's completely tangential to what we're speaking here. So chaos engineering as a practice has a lot of barrier for adoption within organizations. People are generally hesitant about doing chaos, especially folks who are not used to doing it, and people are very apprehensive about doing it on production or pre-prod environments, especially the penultimate staging or pre-prod step that you have, or cluster that you have, which is mimicking all your production traffic, and it's basically a place where you go ahead and put your canary deployments before promoting to your prod. Those kind of environments, people are generally apprehensive to disturb the status quo. They don't want to do chaos, and it takes some time for them to get around to actually going and doing it. But one of the ways to lower that entry barrier, one of the ways to convince the right folks that chaos is a good thing to do, is to actually do it on your observability infrastructure itself. Probably inhibit, do some kind of chaos on your observability infra that is also probably running as a cloud native service on your clusters in the cloud native world, or it could be, if you are in the legacy world, then it could be probably running as its own service out of a VM or something. So you can inject chaos and see what happens. Do you have the right resilience and high availability built into your observability infra? Do you have the notifications coming? Do you have the alerts coming in a correct way? Do you have all the logs being rendered the way they should? Are they all getting collected? Is your messages getting streamed? These are important checks too. And this is very important for upkeeping your production environments. So these are sometimes as critical as your business apps itself. So doing chaos on these components sometimes is something that the folks in the right hierarchy in the organizations might be interested in, and they might sort of give you the permissions to do that. Then you can show the right results there, and take those learnings and those benefits and actually eventually move on to doing it on your applications. So that was a side note. Now coming back to our discussion around steady state, how observability is really critical to measuring steady state. As a chaos framework, as a tool set that you're adopting for doing chaos, you would like to be both generating as well as consuming observability information. And why is that? We want to generate observability information because you have the SRE or DevOps engineers looking at your APM tools, looking at the dashboards when you do those chaos, and you want to correlate your application behavior with a specific chaos event, especially when you're doing chaos faults or chaos injections that are complex. Maybe you're simulating some multi-component failures, or maybe you're simulating one failure after the other in some sequence to sort of build up a larger chain reaction of failures. When you're doing all this kind of exploratory stuff, you want to know exactly how the application is behaving, and you want to map that to a specific chaos event that your tool went ahead and performed. So it's important for us to generate the right metrics, right logs, right events. So your framework should probably be putting out that information. And this is very important. We need to remember that chaos engineering, at least at this point of time, is still predominantly done in a freestyle manner, in a manual manner, exploratory manner. And I'm sure you've heard of game days in many of those previous talks in Chaos Week. Game day is an event where a group of people come together. It's mainly driven by the SREs or the ops folks. They get the developers on board, the support personnel, they get sometimes even the users or the customers on board, they take them along in this journey, say that we are going to inject some fault in this environment. We are going to see what's going to happen, and we are going to do this because this is like vaccination. We want to prevent ourselves from a future outage. We want to check how things are. And while they do these game days, they have a very, very detailed template for doing it. They have already measured, or they've already got a very solid expectation around the impact. They've got mitigation plans ready. They've got aborts auto-configured, and they've got a very good questionnaire to fill out after the experiment is done on what happened, what was the impact, and whether this is of concern, no, etc. So this is done in a very planned and a very organized manner. And this is a manual way of doing chaos engineering. It is practiced by many organizations. And when you're doing this, you're looking at your dashboards and you really want to know exactly what's happening with your chaos tool. What was the event that you did? What was the chaos action that happened? You want to correlate behavior. So we need to generate observability information. But why do we need to consume observability information within a chaos framework? So when you do a chaos experiment in an automated way and not so much in the freestyle way, you would like to, you're not really looking at your system live. So you want to gather and factor in observability information around you, related to your infra, related to your apps. You want to gather and factor this information in, giving you an experiment result. So when you're doing an automated chaos experiment, especially when you're integrating it as part of a CD pipeline, you're doing chaos automatically as part of your CI/CD pipelines, you would like to know what happened to your applications when you did this chaos. Take that information in, process it, and use that to determine whether the experiment succeeded and your steady state hypothesis was proven or disproven. You want to use that information to make a decision on the verdict of the experiment. So it's very important to gather that information. So we need to be able to consume the framework, or the chaos experiments run by the framework should be able to gather this observability information from the ecosystem and use it for validation. And this is a side note that I've put there. Chaos is increasingly shifting left in the cloud native world. You know why? Because look at this pyramid. When you're running something on Kubernetes, there are so many components that are running there, which your application is actually dependent upon for its successful execution. And anything can go wrong. The surface area for attacks just increases. There are multiple points of failures. There are so many interdependencies. It could be the underlying infrastructure. It could be bare metal. It could be cloud. It could be some VMs. Or it could be the Kubernetes services. Kubernetes, being a dense system, has a lot of microservices, a lot of control plane services. You have tooling from the cloud native ecosystem, from the cloud native landscape, for service discovery, for observability, for storage, etc. And then you have your core app dependencies, databases, message queues, etc. And then you have your business app with its front end and back end and user-facing services, etc. So there are so many moving parts here. And people who are migrating to Kubernetes or want to deploy their applications in production on Kubernetes really want to test out and gain confidence in pre-prod environments. And they want to do that continuously, because there are so many changes happening, so many components inside your cluster all the time. You could be releasing your multiple versions of your app, and your SRE team or your services team might actually be upgrading your database versions. Somebody might be upgrading your storage provider versions. So many components are there. They all are getting updated so frequently. So you need to be doing chaos testing continuously. And that means you need to be shifting left, putting it in your CD and not just doing stuff on prod, testing it on prod. So when you're doing this, you're going to be doing it in an automated way. And while you're doing this in an automated way, you want to keep checking your SLOs. You want to keep checking whether your hypothesis is going through or not. So this is what you have. There's another aspect of observability, which we call as analytics. And that's traditionally not counted under observability. But if you want to record your experiment results and compare it over time, maybe build on build, release on release, it's important that you have some amount of analytics built on top of your chaos data that you've gathered. So this is also important, and it helps you grade your resiliency, because your services don't mature immediately overnight, they mature over time. So now we now know what is the importance of steady state hypothesis, what it is, why it is important, why observability is important to measure steady state, what all can be classified as, or what can be the definition of steady state, and how should chaos frameworks be with respect to observability to generate, consume information, etc. So I've built the context. Now, I'd just like to introduce you to some observability hooks that the Litmus Chaos project provides in terms of chaos metrics, in terms of probes, and chaos analytics. Metrics is counting as, or you can map it to our observability info generation part. So these are metrics that Litmus framework generates when you do experiments, and you can use that to achieve what we call as chaos interleaved dashboards. And then you have these probes. Probes are a way to consume information from your ecosystem. And we've tried to factor in the various diverse types of steady state measurements when we created these probes. You could use HTTP probes to check downstream services. You could use command probes to run some specific CLI or run some database integrity checks or some such thing. You can use Prometheus to query how your metrics behave. You can use Kubernetes probes to see how your Kubernetes resources behave and what information is stacked inside them about your application behavior. And then chaos analytics is a way of storing your experiment results and then comparing it over time. So we're going to take a look at these when you do your experiments. So I'm going to show a very quick a demonstration of these probes. Let me go ahead, and I've just stopped sharing my screen so that I can bring up my environment, my setup. Okay, I have done that now. So let me go ahead and start sharing once again. All right, so I've got my screen here. And you're all aware of the Litmus portal. You've seen it in a lot of the previous demonstrations. I don't really have to explain how to install the portal or how you can go ahead and configure it, etc. So that's all something that you know. I'm going to directly go ahead and show you how to use the various capabilities or how you can leverage them in your chaos experiments. I'm going to take a nonlinear approach. I'm not going by the same order that I mentioned in this slide. I'm going to be starting with an HTTP probe. And once I have shown you how that works, I'm going to go ahead and show you some other use cases which make use of the command Prometheus and Kubernetes probes. And during those same demonstration or illustrations, I will also show you how you can generate chaos metrics and use them for achieving the interleaved chaos dashboards. So let's start with an HTTP probe right now. So you can see I have a chaos workflow. I have the Litmus portal here with some chaos workflows already executed. And in my environment, I have what I call as a Hello Service app. So you can look at my screen here. I've got my terminal, and I've looked at the pods and services within Litmus namespace. You can see there is an application here. It's called as the Potato Head application. This is a cool app from the CNCF SIG app delivery team, and they are using it for demonstrating different ways to do app delivery. It's been maintained by CNCF. I just wanted to use this. It's a Hello Service application. It's Mr. Potato with arms and legs. What I'm going to do is I'm just going to kill this pod, which is the source of this Potato Head service. I'm going to do a simple pod delete experiment. And I have just one replica. And this particular deployment has a readiness probe defined with a significant init delay seconds. So when I kill this pod, the service is not going to be active for some time. The image is not going to load. So Let's see what my hypothesis states about this experiment and how we are going to verify that using the probe. I'm going to select the self agent. I'm going to import a workflow, and I'm going to select this workflow called as the weak potato head. And let me just show you what happens when I run it. Let me view the YAML. You look at this, and when you look at the chaos engine, which you know is the main user facing CR in Litmus and contains the chaos definition. So we are doing this chaos against the potato head app, and we're doing the pod delete experiment against it. And this is the HTTP probe. If you look at this closely, it basically states that I need to be querying this particular URL. This is the local service URL for the Potato Head app. And I'm going to expect a response score of 200 OK whenever I query this. And I'm going to query this continuously with an interval of every 1 second. And if at all this fails, then I'm going to retry it and check once again. But my expectation is my application is always alive. So this is traditional simple pod delete experiment. I kill one of the pods, but I expect my service to be still alive because maybe there is more replicas, or maybe there is some kind of load balancer which takes care of all this, and I get my service to be available all the time. But I know that I've just got a single replica, so this is going to fail in this particular instance, right? Because I am doing it in a deliberate way, just to show you how the probe works and make the probe fail. So let me go ahead and run this workflow. So this is going to create a new workflow. You can take a look at the workflow visualization, and these are going to perform the individual steps defined within the chaos workflow. We've installed the application, and it's going to create the pod here. The pod delete pod is going to be rerun now, and it's going to kill the potato head app. One of the things to note here is when the experiment actually starts and the pod gets killed, this particular service is not going to be up. It's up right now, but I will not be able to access it later. And the HTTP probe is going to keep looking for this service. It's not going to be available, and therefore it fails. This is a very simple deployment inefficiency, not having the right number of replicas. But this just illustrates how the HTTP probe works. You could use this to query your downstream applications that you expect should always respond in a certain way. And the HTTP probe allows you to do more things than just do a GET call. In fact, you can take a look at the Litmus documentation for the probes, and the HTTP probes can be used in more interesting ways. You could do post request. You could basically do some complex REST calls and derive the status of your downstream apps and check your hypothesis. So right now, as you can see, the potato head application is killed. It's just come up once again, and the application during this process has come up. This was a very, very quick test. I had a very small period of chaos duration, so it's actually brought things up. But let's see what happens to my probe when the experiment eventually completes. I can check the status of the probe in the chaos result CR that's generated by the experiment. So the result CR gives you the status of your individual probes, individual constraints, whether they were successful, they were not successful, etc. And sometimes you might be lucky that the application recovers so quickly that despite killing the application, your service is still alive. And you might have a successful probe as well. So that depends upon how your application really behaves. So let this particular workflow complete, and let me show you some other important things about these probes. There are some properties that you associate with every probe. There is something called as the probe mode. You can run this probe in different modes. You can do it just at the beginning of chaos. You can do it at the end of your chaos, or you could do it at the edges, at the beginning and the end. Or you could do it continuously, like in our case right now, where you have the probe running in parallel with your chaos experiment. or you could do it just during the chaos duration. The continuous is basically going to do it even during the period when the app is initializing, when the chaos experiment is initializing. So it's basically through the entire duration of your experiment. And this is what you might most likely use for your hypothesis checks. And these probes share some common attributes. There is a timeout for the probe. The probe action could probably get stuck, so you have a timeout, and you have a retry count, an interval defined, and you can also delay the probe execution by some time using the init delay seconds of the probe. So these are some common attributes. And in the examples that I'm going to show you now, I'm going to cover most of these modes. So what we've seen now is the HTTP probe with the continuous mode. And let's see what happened right here. This workflow is actually failed. I can go ahead and take a look at this workflow. The pod delete experiment failed because the probe failed here. You can see the logs, and the logs basically tell you that the access to the particular head service failed because it just had a single replica and it took time. And the same information is expressed by your chaos result. It says the check failed and it wishes you better luck for next time. And the probe success percentage is set to 0. So this is a value that is a ratio of successful probes divided by the total probes that you define. So right now I've just got one probe, it's failed and it says 0. And the verdict of this experiment is failed. When you're running this experiment in an automated manner, you would like to know that this is the check I want to do and this is the verdict that came out. Now let me go ahead to a more complex use case, and for that I'm going to make use of a different cluster. This is basically an EKS cluster. I've got the Litmus services already installed in it. You can see that here. In fact, I also have lens configured to this cluster, so you can see what all namespaces I have. And I'm going to go and do a check against the pods that are sitting in the Percona namespace and the Litmus namespace. And the use case is something like this. I'm going to do a network loss experiment this time, and I'm going to make use of the KTS probe. This is the example that I'm showing you for KTS probe. And as part of this demonstration, I'm also going to show you the chaos interleaving. So we'll also show you how chaos metrics are generated. So the use case is, and the hypothesis is something like this. I'm going to kill one of the Percona nodes. So I have got 3 Percona nodes or pods. This is the XtraDB Galera multi-master cluster of Percona MySQL. It is synchronously replicated. And I'm going to start some load. There's going to be a sysbench load that I'm going to start. And then I'm going to inject a fault, a network loss against one of these XtraDB cluster pods. It's not going to be able to access its peers. And when that happens, I mean, it's not able to access its peers, it's basically going to be thrown out of the quorum. And there is a particular variable or timeout within the Percona DB called EBS suspect timeout, which has a default of 5 seconds. And it's going to see if a particular node is not accessible in these 5 seconds. Then it's probably going to take it out of the cluster because it's going to impact IO. So it's going to do some kind of stone it, shoot the other node in the head, remove it from the cluster, and reform the quorum with the available nodes and continue. So this is the hypothesis that we have, that this particular timeout is adhered to, the quorum is reformed, and my IO does not stop. That's the expectation that I have. And I'm going to validate this hypothesis by doing this pod network loss experiment and setting some probes inside the chaos workflow to verify this. And in this process, we're also going to see how the chaos metrics that are generated by Litmus, let me show you that there are a lot of metrics that Litmus provides. You could use this to annotate your Grafana dashboards or any other system that you're using, and you will be able to get some information here. You can see the Litmus chaos annotation is here. You can use that to get some interleaved graphs. You can see this red area here. It's basically saying that this is when chaos actually happened. So you can correlate your application behavior with a chaos event, chaos injection event that has happened. So let me go ahead and do the chaos on the, let me start the load against Percona. So I have got all the Percona pods placed inside my Percona namespace. I'm listing the pods here, and I'll probably go ahead and exec into my sysbench pod just so that I can generate my load. So I'll just exec into the sysbench pod. This is the one that is going to help me generate some load. I've got a command just for reference that I have placed it here. Let me just copy that. Okay, and I probably need to go ahead and change my IPs, my information here. So this is basically going to be the cluster that's here. Let me go ahead and take the name of my pod against which I'm going to generate my workflow. So I put my pod name, and let me take the password for this particular MySQL instance that's available to me in my document here. So let me use that. Let me start my load run. So you can see that I've started my sysbench load, and with this, the Grafana dashboard that I have for Percona, I've set up the PMM or the Percona monitoring dashboards. That's actually going to start showing some traffic. So let me do this for the last 5 minutes and change the refresh interval to a small value. So you can see there's load now, right? And you can see that there are 3 Percona pods, the XtraDB pods. The size is 3. Now let me launch a workflow that's basically going to do the network disruption on one of the pods. Okay, so I'm inside the portal for this particular instance. Let me create a new workflow. I have some slower internet today, so this is probably taking time to open up. Yep, now I have it. Let me go ahead and proceed with the same steps as I did earlier. I'm going to select a Percona YAML. So this is called Percona DB XtraDB 30 seconds. And I'll show you this particular workflow, how it looks. And it's something that's available here, probably just for better visibility. Let me show it from the GitHub. In this particular workflow, if you look at the chaos engine, I am doing chaos against the Percona application here as defined by the application namespace and label. And I'm going to do pod network loss, and I'm going to use a KTS probe that actually checks if my sysbench client pod is always running. If there's an IO failure, when I do this network loss, this particular client pod is going to crash, and this KTS probe is going to fail. So I have set the right probe here. I'm also going to do this in continuous mode. And I've provided GVR for this pod resource and provided the right field selector and expected that it's always going to be present. So let me go ahead and inject this chaos. I'm going to select a chaos duration that's far more than 5 seconds. So the network loss is going to be injected for more than 5 seconds. One of these pods, the cluster 1 pod, this is the PXE1, is going to be unavailable, and that's going to be kicked out of the quorum. That's my expectation. And you can actually take a look at what happens. So let me go ahead and check if my sysbench client is here. It's still running. And this Litmus portal is basically still installing the experiment. It is performing all those dependent steps. It's going to start doing the chaos in a minute. So once it starts doing the chaos, I need to take a look at the IO, and I want to see whether it really proceeds or it really crashes, and how my KTest probe behaves. And at the same time, we're going to take a look at the Litmus chaos annotations. Yeah, you can see the annotation here. The red area that you see on the graph is when the chaos is actually happening, and it removed one of those cluster pods. It went out of the core. You can see the cluster size. The Percona XtraDB cluster size became 2, and then it's basically come up once again after that. And in my IO, you're going to see a particular period here where the IO was seen to stall for 5 seconds, but not more. The IO continued. The client tolerated this particular stoppage because the other Percona pods were able to proceed with handling these IOs, and they did not have to sync it with the unresponsive replica, which has been pushed out of the quorum. And after the chaos duration is finished, it resyncs and comes back, and the IO continues, which is what we just saw. And at this point, you can also see that the chaos interleaved dashboard is a very useful way of understanding what happens to your application when chaos is in progress. The metric that we've used here is called the Litmus awaited experiment, and that's going to be set to a value of 1. It's going to be set back to 0 when your chaos finishes. And you will see this particular experiment complete, and the KTest probe happened to be successful. So you can see that the KTest probe is gone through, the suspend client was running, and the chaos result says as much. So this is an example for KTest probe. There's another example that I can give you for the Prometheus probes, which are really interesting. And for that, I'm going to make use of a Kafka cluster. And if you look at this particular experiment, I'm going to do a pod delete again this time. And I'm going to do it against a Kafka broker. So I've got a Kafka stateful set with multiple replicas. As part of this experiment, I'm going to generate a test message stream, which has a single topic and a single partition, but that's replicated across different brokers. And it's like multi-replica partition. We are going to identify the partition leader, which handles the IO as part of this experiment, and kill that broker. That's going to trigger a failover. And I need to see if my message queue continues. There is a message timeout that I've set in the consumer, and I want to see if that's honored. And while I do this, while that is my primary constraint, I also want to check some additional metrics, such as I don't want us to see under-replicated partitions before and after chaos. I want the brokers to be fine, and I want the partitions to be replicated with the right replication factor after the chaos is done or before the chaos is done. Similarly, I don't want any offline or unavailable partitions during the course of my experiment. So these are something that I'm going to provide as constraints within my chaos workflow. You can take a look at the workflow here, and this is how the Prometheus probes for that are configured. I have the Prometheus endpoint provided. I have a PromQL query. If you have more complex queries, you can provide that in a file, and you can mount it as a config map within your experiments. And there is a check that I am doing. There's a comparator, there's a criteria, and for the under-replicated partition check, I'm only doing it at the edges. That is at the beginning and end of chaos. But for the offline partition check, I'm doing it continuously. So there's a different metric that I'm checking for that. And I am also going to use the command pro to run a kubectl command. And I could have also use the KTest pro, but I've just used command pro for illustration purposes. I'm running a kubectl command that verifies the status of the Kafka consumer container, and we expect it to be ready always. And the message stream is always going to be continuing to run if this is true. And this is going to be, or rather, the converse is true. This is going to be successful only if the message stream is alive. And I've given a lot of Kafka environment information in the chaos engine. Let me go ahead and show you the Kafka JMX exporter-based dashboard, which tells me the broker count, which tells me how I'm using my messages and how many under-replicated partitions I have, all that information. Let me go ahead and load a chaos workflow for Kafka, which is going to basically use the same procedure that I have been using all along. So let me go ahead and run this particular experiment. Before that, we've not dwelt upon this particular step in our previous demonstrations or previous experiments. So this is basically a way to give some weights or criticality to your experiment. This is particularly useful when you have more experiments as part of a single workflow, and it helps you to derive a resilience grade. And the resilience grade is a weighted ratio of the criticality you associate with an experiment and its success factor provided by the total divided by the total points that you have based on all the experiments inside of the workflow. So let me go ahead and schedule this chaos. I've shown you the YAML. So this is also going to start running now, and it's going to do its steps. And let me go ahead and use lens this time, and let me measure what's happening in Kafka. So you have Kafka namespace here, you have Litmus, you have some new chaos workflows being created. You will have a Kafka load generator pod, what we call as a Kafka liveness pod appear here, who is going to do the message stream implementation and has the producer and consumer containers. And then I'm going to go ahead and identify the partition leader. One of these Kafka stateful set pods is going to be the partition leader, so we're going to kill it. And then we are going to see if our message stream continues and verify the other metrics constraints that we've provided. So let me go ahead and show you what's happening on the dashboard here. You can see very shortly that the chaos is getting triggered. Yeah, the chaos interleaved portion is here. You have the chaos coming up, and one of these brokers is going to go down. You will see a drop here, and you will see the under-replicated partitions turn red because one of the partitions went down. All our topics have single partition with a replication factor of 3, and now one of the brokers is going down. It's become 3 to 2, and because of that, you will have under-replicated partitions. And you can see that the message count actually increases because we are launching this load as part of this experiment. And so that's something that you can measure here. And if I take a look at lens once again, there is this liveness pod. I can take a look at its log, and I am going to the consumer container. You can see this simple message stream is continuing. It's not broken, which means that this particular cluster with the message timeouts that I have set seems to be good enough. I have set 60 seconds as the message timeout for this EKS cluster, and for the CNI that's used here, for the storage that's used here, this seems to be a good value. It's tolerating this failover. But that might not always be the case. You might have more complex situations, because in this diagram, in this use case that I explained to you, we said we are going to target a partition leader. But it so happens that the partition leader is also the controller broker or the active controller that orchestrates the failover itself. So if that is broken, there's going to be a re-election that's going to happen. That's going to have its own impact. So maybe you might have to hypothesize around what's happening when you kill this particular broker as well as part of your experimentation and see whether you're really resilient or not. So these are the various use cases that you can create, the various ways in which you can determine or define your hypothesis in a declarative way using probes in your chaos engine, and then verify them using chaos results and see those execution details on the Litmus portal. I hope this has been useful for you, and the chaos metrics are also useful to you. Analytics is something I just want to touch upon in a second. So we mentioned that analytics is not so much directly counted as an observability element, but it is definitely going to be useful because often you might want to determine how your application resilience has varied over time. And we mentioned about a resilience grade that you're going to run, that you're going to get for a workflow when you run these different use cases. And you might want to check over a period of time how you have matured, how your resiliency has improved for a particular chaos scenario. You could do that using the analytics capabilities of Litmus. So this is basically going to help you to compare workflow results and the resilience grade over a period of time. This is probably taking a little bit of time to load. I have got a different cluster, maybe where I can show you this. Yeah, so there's one more thing that I wanted to just touch upon before we look at actual analytics based on resilience grades. You could actually use the application dashboards here. You could configure your data sources, whatever you saw in Grafana. You could see a fair bit of that within the Litmus portal itself. You can do checks using your Litmus portal. You can monitor your dashboards. This particular portal is basically showing the graphs for sock shop based experiment that we have done. It's going to take a little bit of time to load real-time data here. Let me come back to that. Before that, let me see if my analytics is able to load for the workflow that we just ran. And I think this is probably just due to my slow internet speeds. But yeah, let me come back here. You can see the same dashboards that you saw in Grafana. This will allow you to monitor stuff within your portal. You might not have to go out. You can construct dashboard JSONs just like you would for Grafana here. It uses Plotly. And let me go ahead and select information that I want to see for today, which is when we have actually run the experiment. So there will be some chaos interleaved dashboards that you can see. You can see these highlighted areas. These highlighted areas are basically the period when the chaos has happened, and you can find out information about what's happened, whether it was successful, whether it was not, what your metrics are saying for this particular app. You can verify that within these dashboards as well. And you also have a table view of whether the experiments passed or failed. And you could correspond these legends to the interleaving inside of your dashboard. And you could also get useful information by comparing chaos reports. So this is where you have reports. You can select this and you can see the analytics. This is basically going to show you some graphs of your resilience grades, and you can compare it over a period of time. So this is what we have for your analytics. You can even go ahead and download reports. You could probably basically compare more than one workflow if you have them, and then you can download a PDF report or an HTML report around your chaos results, and then use that in some analysis that you post processing or analysis that you're doing on your experiment. I would have liked to show you the graph that comes up to show the resiliency grade, but it's taking a little bit of time. So I'm sorry about that. Anyways, I think I've covered most of what I wanted to show during this demonstration. If there are any questions that I can take, that would be good.
Hey, Karthik. Well, great talk. Thank you very much. So great. I think there was great insight in there. Thank you for sharing your experience there. I love the insight about defining a steady state at the beginning. I think it's very interesting. And also, I cannot agree more with you over the importance of observability. Like, it's very important. It's been a very instructive and comprehensive demo as well. That's good. And while we wait for a question, maybe I can ask one myself. So you were just saying that you can import directly JSON from Grafana dashboard inside Litmus, right?
Mm-hmm.
Cool.
Not exactly the Grafana dashboards, but you've got some very similar structures
Okay.
If you take a look at this dashboard, you have the JSON model here. So the Litmus portal's workflow dashboard provides a JSON that's very similar to the Grafana JSON that you have. I could share some examples probably as part of my slides, or some links that I can provide. It's very similar to the Grafana dashboards.
That leads to my question actually. So in Grafana, you have some community dashboards shared. Is there such a place for dashboard we could reuse in Litmus somewhere?
Yes, you could. We've made a few dashboards. Yeah, finally the analytics is opened. Yeah, in good time before we end it. Just to come back to the question, we have some sample dashboards for Kubernetes and for SockShop. As I showed you the SockShop one, but there's the standard node exporter and the K-test metrics dashboards that are available. They are in the Litmus repo. You could make use of them, or you could use them as references to construct some custom dashboards of your own. Yeah, we do have a couple of examples. We are in the process of bettering the documentation for our monitoring, and we will place more samples for the Litmus dashboard JSONs.
Okay, and also about your dashboards in Grafana that you use to follow your experiments. Do you think there's a way to share Grafana dashboard that helps follow Litmus experiments somewhere? So I guess you have couples in your bootcamps in GitHub, but I think it's probably a good idea if there's some place we can share dashboard to follow experiments from Litmus based on different technologies.
Yeah. So there are some Grafana dashboards. There are a few in bootcamps, like you mentioned. There's one for Grafana, for Kafka, for Percona, etc. There's one available for SockShop as well, the standard ones that you can use on Grafana. But there are also some off-the-shelf Litmus dashboards that you can use to construct a view of how your experiments have gone, not specifically related to your app behavior, but you could use some of these other Litmus aggregate metrics, which tells you when certain experiments started or ended, and whether they were successful or no, and cumulative details of how many times a particular experiment passed or failed. You have some other metrics as well, and there are some dashboards which show you this information. We will probably share that links.
Okay, cool. Well, I don't see any question yet on the chat, so yeah, sadly I don't see any other questions there on the chat. But thank you very much, Kartik, for the presentation. That was great. So the video recorded will still be available on YouTube, and further people that watch it could ask questions in the commentary of the video, so it might pop up later. And well, thank you very much, and thank you everyone for attending this Chaos Week and this last talk of the Chaos Week.
Thank you. Thanks to the Chaos Week team for giving me this opportunity. I thoroughly enjoyed being on the conference, and all the best. Stay safe, and yeah, meet you all in the next event.